What's going on, guys? Welcome to another AI session. So today we will be going through the code base of nanoGPT. nanoGPT is an implementation of a character level transformer referencing the attention is all you need paper. So this GPT was created by Karpathy. For those of you who don't know, Andre is actually an AI researcher at OpenAI, and he's also one of the co-founders. He used to be the director of AI at Tesla as well. And he has been one of the many role models that I have lately. So I've been really inspired by his work, and today we'll just go through his very awesome nanoGPT code base, and we'll explain it from a beginner's level, since I'm also starting new in this field. So for example here, what he actually did, the kind of GPT we have here is a decoder only GPT. So if you look at the transformer paper here, it has an encoder and a decoder, but the nanoGPT is actually just a decoder only, because for us, we're not trying to translate anything, because this transformer was built for the purpose of translation, translating one language to another. So we are not translating anything. All we're doing is we just want to imitate the input of our data. For example, the data we'll be using is a Shakespeare's data here. And so what we want to do, we want the model to be able to predict the next token, since it's a low-level model transformer, a character level transformer. So all it does is just predict the next token or the next character, and thereby with enough training, it will be able to mimic the input text here, as we see here. So he actually used a very simple approach, which is very easy to understand. So without much ado, let's just dive right in. So for example here, first we are actually getting the data, which he already placed on his GitHub repo, but I've downloaded it, so I already have it here. So I have also created a Chinese version of it in order to see how the model does with a Chinese data input. And this is the English version of it. So it's just like a script between, conversation, just like Shakespeare. I don't know much about literature. Okay, so let's get right back into it. So for example here, after getting the data, after downloading the data, but for us, we'll just open it here. So you open it and then we read it, and we'll just read the data directly. And then from there, we try to print the length of the data, that is the number of characters that are in the data. So as you can see here, we have up to 100 something thousand. No, not 100. We have up to 1,100,000 characters. And so the next step is to actually print the first 1,000 characters. So we print them just as they are in the input data. And this is what it will give us. And then after that, we try to actually get the number of unique characters in the data set. So for example, here we are calling a set on a list, just so that we do not repeat the characters we are looking for. So we pass in a characters and then we call a set on it in order to avoid repeating the characters. So that will make it unique. And then we get that. After that, we get the length of all the characters, and then we just print them out. So we have 65 unique characters, and these are all the 65 unique characters. I believe they're all available on our keyboards. Yeah. And then the next thing he did, he made this simple implementation of converting a character into an integer, that is the second level in the transformer, like to tokenize, or it's called tokenization. So in order to assign a number, because the transformer don't actually take the raw text input, it doesn't read that. What it actually sees is just an array of numbers, So for example here, we are printing, we are encoding the word here, hello transformer, and then we are decoding it. So when we encode it into integers. So for example here, this line is actually string to integers. So we are trying to loop through the number of characters by referencing the index of those characters. And then we just want to store that into a dictionary. And then after we store that into a dictionary, then we can simply use the encode function here in order to encode our input data or our characters. So for example, here we're doing the same. For the decoder, we are doing the same. So it's just the other way around. So in this case, we are trying to get the integers to string, and then we loop through the input data, and then we convert that, and then we join the output of that text. So for example here, hello transformer will give us this number of characters. So this is like the second level for when you look at the transformer paper. So tokenization here. And then next up is actually to get the length of our data. That is, we are trying to take this chunk of data and then passing them into a tensor. So for example here, he's actually importing PyTorch. So we're using PyTorch here. And then we try to call torch.tensor on the text on our input, so that we can just reproduce a tensor. For example, here we are reproducing a tensor of the first 1,000 characters. So if you're wondering what a tensor is, it's just an array of integers here, as you can see. It's just an array of integers. So 64-bit actually. And then here we're just giving out the random values of the random the random integers of the first 1,000 characters. So next up, what he did is actually try to split the data. So here he's splitting the data into training and validation data, as in old school deep learning. So 90% of the data is actually training, and then the rest is validation data. And then in the next step, he's making use of new words here that we don't know. So block size and train data. So the block size is actually the size of our context, or the size of our input. So for example, here it will be 8. He's calling an 8. And then next, in our training data, we would like to get the block size of the first 9 characters. And this will actually result in, it will actually result in these numbers in the form of a tensor, because we've already called tensor on our data there. So next, what he's actually doing here is trying to, because since the transformer, when they're training this transformer, they're not actually giving it all the data. So for example, our input data here, they're not actually passing all of this chunk of data to it. Instead, they are dividing this data into batches. So batches of chunks of data. So they are dividing it, so they're taking them randomly. So for example, in our input data, in our data here, raw data, maybe they might just take like this line from here to here and then feed it into the transformer, and then the transformer will have to get trained using this one and then predict. So that's how they are doing it. So they give the transformer this data by batches, and then making use of the block size here as well. So in order to do this, what he did is create an input variable here, which will take the first block size, the block size itself, that is the length of our chunk of data, and then an output, which will be the prediction. So this is where the prediction will take place to predict the next character. So in that case, we'll have to loop through the block size, and then our context will be the input plus 1, and then we have a target, which will just be within that loop as well. So for every target here, what he did is just print for the first, for this block size of 8. So he just prints the target. So for example, for tensor 18 here, we are getting a target of 47. And if you have 1847, you're getting 56, and so on. So this is actually important in order to how do you call it, improve the evaluation of the cross entropy loss of the model. So it's important because what we're doing here is trying to balance our loss and our validation, right? So this is really, really important to do. And then the next part here, what he actually did is try to create a whole, let's say, a whole function for implementing what we just did. So in that case, we want to get a batch. So that batch will be split into what? Training data. So if it's training data, you call on train, else it will be validation data. And then next, what he tries to do here is, since we will be feeding the transformer random input or random chunks of data, so he called on its IX variable, which would just take in random chunks of data, making use of the batch size. And this will happen with the random offset. A random offset, that is the next token, to predict the next token. And then next, so basically what he did is just stack these inputs. So the inputs are stacked, and then the same thing is done for the output Y. So they are just stacked on top of each other like that, referencing the block size, of course. And after that, then next, he just made a simple, So when this is run, for example here, when this is run, we can simply see here our output. So for example, this is our input. This is X of B, that is the batch that we've input into the transformer. And then we have our target. And then next we have our output. So for example, 24 here, what will be the next? After 24, it will be 43, and then 43 to be 58, and so on. So basically, this is what this this chunk of code is actually doing. So the get batch function. So all it does is just split the data into two, and then it will then feed the data, get random parts of the data, and then feed it into the transformer, just like that. So that is what that line did. And then next, here we are actually printing our inputs. This is our input to the transformer. So this is what it will be for a batch size of 8. So it will be a 4 by 8 tensor actually. So tensors are just basic arrays, or in this case, they are arrays of integers, multiple arrays, as you can see here. And you can see it kind of looks like a matrix. It's actually a matrix. So now that we've got our input for our transformer, which is just an array or multiple arrays of integers here. So next, what we'll have to do is to feed this input into a neural network. So what he did here, he made use of the simplest neural network, because since this is a very low level GPT, so which he made use of the bigram language model. So for those of you who don't know, it's a model that actually predicts the next token, which can be a token, can be a word, it can be a letter or syllables, and so on. So that is what it actually does. So he actually made use of the bigram language model from PyTorch, so he doesn't need to write a whole, write it from scratch. So he just made use of it here. So he's calling it's a subset of the module, the neural network module. So he's just calling it here. And so we saw some new words here. For example, we have logit, and then we have, which one again? We have something like cross entropy, which we just use to calculate our loss, which is important for our for evaluating the model's performance. And so basically, logits are unnormalized log probabilities for each token. So they are just raw probabilities of a token. So that's what they are. And so the model actually makes use of this logit, and then it uses the probability of this logit in order to calculate the cross entropy loss of the model, which is used to measure the performance of the model. So let's look what inside the hood of this bigram language model. So for example, here inside of our init constructor, what he's doing is actually just creating an embedding table, and then this table is vocab size by vocab size. So for every input to the bigram model, so this table will be referenced, and then it will just pluck out that particular row that is being required. And then next, it has a forward function here. So in our forward function, what he's trying to do is to shape the PyTorch bigram language model to meet our own, or his own his own structure. So what he wants to do is to create an array of B by T by C. So for example, B means the batch, and then T is the time, and then C is our channel actually. So but for in PyTorch actually needs this C to become the second array here, or the second item in this array here. So that's what it wants according to the documentation. So if we look, I think, okay, yeah, according to the cross entropy documentation here, so it wants it to be in the second value in that array. So what he did here is actually try to prime the model in order for it to meet the requirement of PyTorch bigram model here. So he was able to do that by just stretching the array, the first two arrays. So he just stretched them by dotting them, and then the next array will then be the channel. This is actually fun to see. And then next, he's just setting the target, and then just calculating the cross entropy loss using our logit and our target, and then we just return that value. So this bigram model actually calculates the loss, and then it actually generates values. So this is the generation block. So for example, here we are actually generating a sequence of tokens from our input, and then of course the array is our IDX, that is our ID for each generation. So it's between 1 to maximum number of tokens here. So between 1 to maximum number of tokens, which actually is good for the transformer, because the transformer should be able to predict the next token, whether it's just a single input or it's multiple input. So that is what he actually did here. And then another important aspect is making use of the softmax. So for those of you that know, softmax is actually used to normalize our probabilities, that is the values that we get from our logit, so that it doesn't be negative. So it will normalize it to 1. And that is what that line is actually doing. So next, the generation will just predict, and then we will just, use the logit and then our loss, cross entropy loss function, in order to predict, to feed that into our bigram model, and then in order to generate the text. So let's just generate that and see. So as you can see here, for the first, let's say 100 tokens, you can see this is really, really random, and it doesn't actually look like our input data. So what we'll have to do here, let me see. Okay, so if we try to, let's say, increase the number of maximum tokens, we can see that our model is actually improving. So the expected output here, as you can see, for example, our gradient here is our loss here is 4.8.785. We're actually expecting much less than that, but we'll come into that later. So still the text that is being predicted is still random. And next, what he did is to create an optimizer. So what does this optimizer do? So what it does, it improves our calculation, or the calculation done by the bigram model, because the bigram model is used to calculate the cross entropy loss, right? So it actually optimizes that value. So he's making use of the Adam W optimization function, which you can read more about. So it's a very popular function there. So he did that for the first. Should actually print. Okay, yeah. And then we have a learning rate of 1 exponential to the minus 3, which should be, you should actually specify a learning rate for that, for the Adam W to work properly. And then next here, he actually assigned a batch size, which is just the chunk of data that we want to feed into the model, a batch size of 32, and then he loops through for an iteration of, let's say, 10,000. Let me just reduce this to 1,000 because it will take longer if it's 10,000. Okay, so batch size, and then we use our get batch function that we've just created, and we are taking the data from the training data set. And then next, what he did, and then next what he did, we can actually clear this. Let me just clear out. Yeah. And then next what he did is actually passing the because these are input and output, right? So XB and YB, input and output, and that is what the get batch function needs. And then he's assigning them to that. So next we have our logit and our loss, which will be used to calculate our loss cross entropy. And if we do this for the first 1,000 iterations, let's see what our loss will be, because we're actually expecting our loss to be, let me see. So we are expecting our loss to be minus the log of, oh no. So minus the log of 1 upon 65, because our maximum batch size, our maximum length of data is 65 unique characters. So minus 1 of 65, and then next, that should give us something like, let me see, should be 4 point something. So after we've fed our tensors into our transformer using the bigram model, and now as you can see, we have this random predictions here. We have this, these are just random predictions, and this is not what we want because it doesn't look like our input. So what he did here is he created an optimizer, and he made use of the Adam W optimizer, which is a very popular optimizer, and then which has a learning rate of 1 to e minus 3. So these are just random constraints for the optimizers to work well. And then next, what he did, he gave the transformer a small set chunk of data, which is a batch size of 32. So then he loops through, let's say he does an iteration of 1,000 in order to get the loss. Because what we actually want, if we look at our model, our loss should be around this value. So it's 1 negative log of 1 divided by 65, because 65 is the maximum number of characters, unique characters in our model, in our data, So the loss will be this one. So we want our loss to be around this value. So he's actually training the model, the bigram model, to predict this loss. In order to do that, you have to iterate through the model, and then Next, what he did is make use of the optimizer we've just created and then pass a zero gradient on that optimizer in order to normalize the value. And then next we call a back propagation for it. And then after that, we print out the loss. So here we are having 2.9, which is actually not what we want. But let's see one more time. I think if you increase the range, the number of iterations, you should be able to get pretty much close to that value. And it should be under. So mind you, the loss should be under this value. So our 2.9 was not that bad, but let's try it one more time and see. And while that is running, so as you can see here below this, here, what we're doing is simply just generating the text now after doing some optimization to our loss function. So here he's just generating the text. So we have a maximum tokens of, let's leave it to 100 for now, of 100. And then we just want to predict with this maximum number of tokens, we just want to generate the text. And let's see. And we're making use of our decoder function. Okay, that's not bad. So let's just print those out and let's see. Okay. So this doesn't actually look like our input data, but it kind of gives us a clue. So it's like taking just a chunk of the paragraph, and then just let's try it one more time. Okay, that's not bad. Nothing here makes sense. So yeah, so we'll stop here for today, and then in the next video we'll see how he makes use of the self-attention method to actually get the tokens to talk to each other. That is for a more accurate prediction. So that's where in the transformer paper they made use of the self-attention block, which is actually one of the most important, or is the most important part of the paper. So that's why the paper was titled "Attention is All You Need." So the self-attention mechanism is actually a way in which the tokens speak to each other, and they're able to validate the probability of each token based on the previous ones, and then be able to predict the next token using those calculations. So for today, we'll just stop here. And if you want to read more about this, you can go to his repo. So the nanoGPT repo is out there, and it's very popular. And as you can see, it actually gives a performance equivalent to that of GPT-2. So it's pretty much a good paper. So before we finish here, I just want to do the complete to run the complete code. So he actually broke it down into different steps, and then there's a complete version. So for example, this is the complete code base. I'll just run this so that we can see. We'll try to run this on the Chinese data set. I found out that using the Chinese data set, it actually predicts well as compared to the English one. So let me just try to adjust the value of our, okay, yeah. Let me just change this to, should be CH. And then let's just say we do a 1000 iteration and see, because we don't want this to take too long. So yes, as you can see here, the training for 1000 iterations was actually impressive. So as you can see in the Chinese, you can actually make sense of what the model is saying. So you can see, like, for example, this one, DE Gongming. So you can see in our input here, DE Gongming. So you see, if it was in English, it would have been really hard to predict. So I believe the advantage here is actually because the characters here in the Chinese version, they mean a lot. Whilst for us in English, they're just letters, so they don't have any meaning. So yeah, so I believe it outperforms the English one when it comes to this level. Okay, that'll be all. Thank you for watching. See you in the next one where we'll talk about self-attention. And yeah, leave a like, comment, and subscribe. Thank you. 谢谢.